Good day, class. In this video, I will teach you orientation or rotation matrix. Okay, so after learning the DH frame rules and the way of assigning frames on our kinematic diagram, okay, we will study how our mechanical manipulator moves. Okay, so we have here an example of an unarticulated manipulator, a simulation of an articulated manipulator. So as you can see, it has a frame at the end effector. Okay, the frame at the end effector indicates where will our mechanical manipulator move. Okay, so as you can see, as our mechanical manipulator moves, uh, the end effector is changing its position and also what you call its orientation. So the term orientation means how your mechanical manipulator or how your mechanical manipulators and effector angles at space or angles in space. Okay? That's why it is also called rotation because it has rotation angles. Then, as you can see also, as the mechanical manipulator moves, the position of the end effector changes. So the term used for the change in position of the end effector is also called position or displacement. Okay, so the position is described in a mathematical model or described as a position or displacement vector in mechanical modeling. While for orientation or rotation, it is described using orientation or rotation matrix in mathematical modeling. So with the help of the position and the orientation or rotation mathematical model, we can make our mechanical manipulator move. Okay, so the rotation allows or the rotation matrix allows the movement of each joint of our mechanical manipulator, especially if it is revolute. While position or position displacement vector allows the movement of the joints of our mechanical manipulator, especially if it is uh, prismatic or prismatic joint. But this mechanical manipulator, which has only revolute joints, allows both position and orientation to move. Okay, because position and orientation or rotation uh, is simultaneously happening or simultaneously applying in this mechanical manipulator. So first we will learn about orientation or rotation, then position for our position in the next days. Okay, so the use of orientation or rotation is to move the revolute joints and to orient the movement of our mechanical manipulator. So it helps or it is used to make our mechanical manipulator targets its workpiece. So for example, here, these mechanical manipulators are painting this car. Okay, so these mechanical manipulators are targeting specific areas in this car to paint. So orientation is what they use to target those specific areas. In this left example, this mechanical manipulator is used to weld. Okay, is to weld a workpiece. So the orientation or rotation is used to make the mechanical manipulator to help the mechanical manipulator targets its path of it's the welding path of its workpiece. Okay, so let's go to our OneNote to derive the principle of rotation. So be reminded, class, that in an ideal mechanical manipulator, okay, there is a 6 degrees of freedom in an ideal mechanical manipulator. So those degrees of freedom came from the first 3 degrees of freedom. Okay, the first degrees of freedom, that is doing the translation. Okay, doing the translation, and another 3 degrees of freedom for the orientation. So that's why an ideal mechanical manipulator has 6 degrees of freedom. So 3 degrees for translation or positioning of the end effector, and 3 degrees of freedom for the orientation or rotation of the mechanical manipulator. Okay. So before I teach you the principle and the derivation of orientation, I will teach you first the principle of projection. So we will use projection to derive uh, the mathematical model of a rotation. So first, I will draw it a yellow 2D Cartesian coordinate system. Okay. Then, inside this Cartesian coordinate system, is a vector, red vector arrow that we will name V. Okay. So this V vector has no description yet. So we will describe V vector. So we will describe V vector using the principle of projection. Okay. So to explain the principle of projection, we will use a flashlight, an imaginary flashlight. Okay. At the top of the V vector, and another imaginary flashlight at the right side of the V vector. Okay. So when the light strikes the V vector, it will create a shadow at the x-axis. Okay. The same with the light from the right side. It will make a shadow at the y-axis. Okay. So this is the x-axis, and this is the y-axis. So we will name the shadows projection A at the x-axis and projection B at the y-axis. So using these projections, we can describe vector V using the coordinates of x and y, and the coordinates of this x and y are the projection A at the x-axis and projection B at the y-axis. So we can describe V. Okay? Can describe V using the coordinates of x and y axis. We can also describe vector V using trigonometric functions because there will be an angle. Okay? There will be an angle between vector V and the x and y axis, especially at x-axis. So the angle at x-axis, we will name it theta. Okay? So this will make a triangle. Okay. This will make a triangle, a right triangle. Okay. So using the principle of a trigonometry, we can describe this using the trigonometric function tangent theta, which also means the opposite over adjacent. Okay, the opposite side is the B at the y-axis, and the adjacent is A at the x-axis. So we can describe the position of V using the projection A and B at the x and y axis, and its direction. In mechanics, we call this direction. This is a trigonometric function. Okay, this is also called the orientation or rotation because we use here a rotation angle. Okay, so we can describe it using trigonometric function, and we use the tangent theta or the opposite over adjacent. Okay, so this is the principle of projection. So we can use projections to describe a vector. Okay, so this is for 2D, okay, 2D Cartesian coordinate system. But in robotics, we are dealing with 3D space. Okay, 3D space with 3 planes. So we have here 3D Cartesian coordinate system. Okay, again with V vector. Then projections at the x-axis, projections at the y-axis, and projection at the z-axis, namely A, B, and C. So we can describe the position of B as A, B, and C. Okay, so to describe the direction of V or its rotation or orientation, okay, we will use a different method. Okay, we will still use the method of trigonometric functions. We will still use the principles of trigonometric functions, but the indifferent method. So we will derive uh, the mathematical model of rotation orientation, and it is called the rotation matrix. Okay, so rotation matrix. So I will draw these projections at the smaller scale, or at the larger scale, sorry. So we will have here first a frame. Okay, so we will name it now a frame instead of a Cartesian coordinate system. So we will name it a frame because it is the term we used in robotics. Not okay. Okay, class. So Z0, Y0, and X sub 0. Okay. So we will name this frame as frame 0. Okay, because all the subscript of our axes are 0. Okay, then so we will have a projected frame, namely frame 1. Okay, so So we will have an x-axis here, x sub 1 axis here, y sub 1 axis here, and z axis here. Okay. So we will name it as z sub 1, z sub 1, y sub 1. Okay. Y sub 1 and x sub 1. Okay. So to derive our, okay, so let's make this like this. Okay. So to derive our rotation matrix, okay, we will need to have a rotation angle to rotate an axis. So we will rotate first at the axis of z0 and z sub 1. Okay. So if we rotate at z0, z sub 1, there will be a movement at y sub 1 and x sub 1. So we will not move our base frame or our world frame, which is y0, which is frame 0. So what will happen at y sub 1, it will be like this, and x sub 1 will be look like this. Okay. So they moved because of the angle theta. Okay. So when the axis of x sub 1 and y sub 1 moves, it will also create an angle. So the angle created is the same angle that make them moves. Okay, so it is theta. Theta is the angle that make them move. So this will also be theta. Okay, so this also theta, and this will also be theta. Okay. Then just like at the 2D, to the core to the coordinate system, it will create a triangle, a right triangle. Okay, so there will be a right triangle here. Okay, so this is our frame zero. We have here a frame zero and its projection, which is frame one. Then frame one was oriented. That's why it or rotated. That's why x sub 1 and y sub 1 moves counterclockwise. So be reminded, class, or please remember that we are rotating counterclockwise. So if we are rotating counterclockwise, our rotation angles are positive. Okay. So using this new drawing and the principle of projection, we can say that rotation matrix is how the rotation of frame n, the frame n is the frame 1, if n is equals to 1, is projected on frame n minus 1. Frame n minus 1, if n is equals to 1, then our frame n minus 1 is frame 0. So this is how the rotation of the frame 1 is projected on frame 0. So we can describe it using a 3 by 3 matrix that is called rotation matrix, where the column describes the projected frame, while the rows are the reference frame. Okay, so here our reference frame is 0 frame and our projected frame is frame 1. Okay, so using this model, we will derive a rotation matrix. Okay, so to derive a rotation matrix, I will copy this again and paste. We will use this to derive a 3 by 3 matrix. Okay, so our reference frame is frame 1. So the x, y, and z at the top are x sub 1, y sub 1, and z sub 1. While our x, y, z at the side is x sub 0, y sub 0, and z sub 0. Okay. So I will redraw this side of our frame where the axis of y0, x0, and the vector and the axis of x sub 1 creates a right triangle. Okay. So this. Okay. This new drawing is the same with this, but now we are looking at it at top view. Okay, we are looking at it at top view. Okay, so please be reminded. Okay, so what we will do here, we will describe the projection of x sub 1 on x sub 0, y sub 0, and z sub 0. So let's erase this. Okay, so what does that mean? So we will look at x sub 1 at our matrix, and x sub 0 at our matrix, and we will look at the x sub 0 and x sub 1 at our right triangle. Okay, so if you notice, there are one at each side of the right triangle, because we will assume here that the sides of the triangles of our right triangles is 1. Okay, so this is always an equilateral right triangle. Okay, so the same with the axis, we will consider them as 1. We will assume they are their measurement is 1 unit. Okay, so this is 1 unit, this is 1 unit, this is 1 unit. Okay, so to describe the projection of x sub 1 to x sub 0, we will use the trigonometric function. So we will use the principle of SOHCAHTOA. Okay, so x sub 1 is projected to x sub 0 using the using the trigonometric function cosine 0, or the adjacent over hypotenuse. So x sub 0 is our adjacent, x sub 1 is our hypotenuse. So if we understand that cosine theta is the projection, cosine theta is the description of projection of x sub 1 on x sub 0. So we will put cosine theta at the first element of our 3 by 3 matrix. Okay. Next, now we will look at x sub 1 and y sub 0. So we will describe the projection of x sub 1 on y sub 0 using again katawa. Okay? Y sub 0 is the opposite. Okay, the opposite side. Okay? This is the opposite side, but it's at the y sub 0 axis. Then again, the hypotenuse is x sub 1. So we have here the opposite over hypotenuse. So this will be equals to sine theta. So the description of projection of x on x sub 1 on y sub 0 is sine theta. Okay, next. So the projection of x sub 1 on z sub 0. So as you can see in our figure, in our right triangle, we don't have x sub 0. So x sub 1 is not projected on z sub 0. So we will just put 0 at the element of x sub 1, z sub 0. Okay. So we have now a column at our we have now a first column at our 3 by 3 matrix. Okay. So next for our y sub 1 column, we will use this side of our or this part of our smaller or sorry of our frame 0 and frame 1. Okay, so I will redraw it and it will look like this. Okay. So we will also have a right triangle. Now it is still at the plane of the x0 and y0, but now the y sub 1 is at the negative side of x sub 0. Okay, so we will use here the principle we used in DH frame rules. So the right side, which is x sub 0, is the right side. This is the positive side, and the opposite side is the negative side. So y sub 1 is at the negative side of x sub 0. So it means we will have here a negative trigo function. Okay. So y sub 1 is our hypotenuse. Okay. Then this side is our opposite side. Okay, this is our opposite side, which is at the negative x sub 0 axis. Okay, so we will have here opposite over hypotenuse, which is equals to sine theta. Okay, but because y sub 1 is at the negative side, so because y sub 1 is at the negative side, so we will have here a negative x sub 0 over y sub 1. So let's bring the negative sign to the trigo function. Okay. Now we will have now a function we will have now a description of a projection of y sub 1 to x sub 0. Okay. So this will be negative sine theta. Okay, negative sine theta. Next, the projection of y sub 1 on y sub 0. So y sub 1 is the hypotenuse and y sub 0 is the adjacent. So we will have here adjacent over hypotenuse. So we will have a trigo function of cosine theta. Okay. So the projection of y sub 1 on y sub 0 is cosine theta. Then the same with our previous drawing. Okay, this drawing has no z sub 0 whatsoever. So the projection of y sub 1 on z sub 0 is simply 0. Okay, so for our last column, the z sub 1 column. Okay, so we will go back to our first draw, to our original drawing of frame 0 and frame 1. So based on our drawing, z sub 1 is at the axis of z sub 0. They are overlapping. And the rotation happens at the axis of z0 in z sub 1. Okay? So z sub 1 is not at the, or z sub 0 is not at the plane of y sub 1 and x sub 1. So it means z sub 1 is not at the plane of x sub 0 and y sub 0. So it means z sub 0, z sub 1 is perpendicular both to x sub 0 and y sub 0. So there will be no angle of projection. So their elements will become 0. While the projection on z sub 1 to z sub 0 will become 1. So why 1? Because again, we assume that all sides, even the axes, are measured as 1 unit. Okay? So this matrix is what you call the rotation matrix. So this is not just a rotation matrix. This is called a Z rotation matrix. Okay. So this is called a Z rotation matrix. So why Z rotation matrix? It is because the angle theta, or the rotation angle theta, rotates at the z axis, or at both at z0 and z sub 1 axis. So it means there will also an x rotation matrix and y rotation matrix. So this is just for z rotation matrix. So we will have also x and y rotation matrix. Okay. So to have an x and y rotation matrix, we will also must repeat what we have done on the z rotation matrix. Okay. But for now, I will give the standard notation or the standard formula of the X rotation matrix, Y rotation matrix, and the Z rotation matrix that will be used for the computation of the rotation matrices of our mechanical manipulators. Okay. So the variable or the notation used for rotation matrices are what you call the R. Okay, a capital letter R with superscript n minus one. The n minus one stands for reference frame, and a subscript that stands for projected frame. Okay. So let's have a sample of how to use this notation or this symbol. So for example, we have here a SCARA manipulator. Okay. A 2 degrees of freedom SCARA manipulator. This is a 2 degrees of freedom. This is not the 3 degrees of freedom one. Okay, this is a 2 degrees of freedom. Be reminded. Okay. So a mechanical manipulator has its own rotation matrix. Okay. So we will describe its rotation matrix as R. Then our reference frame must be the base frame. Okay, so our base frame is named as frame 0. Okay, because it is our first frame. The start of our numbering is from 0. And if n is equals to 1, then 1 minus 1 is equals to 0. So that's why this is 0. Okay, then our projected frame must be the frame of the end effector. So the name of our end effector frame is frame 2. Okay? They are all okay, the axes are labeled with 2, with number 2. Okay, so that's why the projected frame is 2. So this is read as R02. Okay. So this R02 describes the 3 by 3 rotation matrix of our SCARA manipulator. So to derive the 3 by 3 rotation matrix of this SCARA manipulator, we will not use or we will not do what we have done on this uh, first frames of 0 and 1. Okay, we will not do this because the frames of these SCARA manipulators are not the same with the arrangement of these two frame. And we have here three separate frames. So what we will do here, we will derive the rotation matrix inside the other rotation matrix inside our mechanical manipulator. So as we can see, we have here three frames. So we have here three frames. So we have a rotation matrix for frame 0 to frame 1 and frame 1 to frame 2. So this will make a two separate frames. So let's name the first frame from frame 0 to frame 1. Okay. So again, the superscript will be the reference frame. The reference frame is the frame 0. Then the projected frame. Okay, the projected frame is the next frame, which is frame 1. Okay, so it will be 1. So as you can see, class, the R01 is equated to R02. So it means we will have here an equation. Okay, we will have here a multiplication operation of matrices. Okay, so next is the rotation matrix from frame 1 to frame 2. So again, we will have here an R, capital letter R, and then our reference frame is frame 1 because we started at frame 1. Then our last frame that we will become our projected frame is frame 2. Okay. So as you can see, this is a multiplication of 3 by 3 matrix. Okay. So if we multiply these two with each other, we will have an R02 matrix. Okay. So it is obvious because if you multiply R01 to R12, the subscript subscript 1 at R01 will be cancelled, and the superscript at R12 will be cancelled. So we will have R02. Okay. So the same with a mechanical manipulator with too many frames. Okay. So for example, this we have here a Cartesian manipulator with too many frames. We have here 5 frames. Okay. So the rotation matrix is described as R04. Okay, R04. So the first frame is R01 multiply to the next rotation matrix. Sorry. So this is the first rotation matrix R01 multiplied to the next rotation matrix R12. Then multiply to the next rotation matrix R23, and lastly multiplied to R34. So be reminded, class, this is multiplication of 3 by 3 matrices. If we are multiplying matrices, the succession of matrices is important. So the succession and the arrangement of the matrices is important. So we should not put, or we should not multiply matrices like multiplying like this, or multiplying like an ordinary number. So if you multiply matrices, it should be at this order. It should be based on the rotation matrix of the whole mechanical manipulator. Okay. So as you can see, if we cancels the superscript and subscripts, we will arrive at the rotation matrix of the whole mechanical manipulator, R04. Okay. So for the next video, we will derive the R01 and R12 for our SCARA manipulator. So what we will derive is the R01 and the R12 before having the whole rotation matrix, which is R02. Okay.